All right, so welcome everyone to another GDG AI for Science workshop. Today we're going to be learning all about the Kaggle platform. I'll try to keep everything in the context of how we can sort of leverage the platform in research, but we're also going to learn some fundamental data science skills and hopefully give you the confidence to learn how to humble yourself on the leaderboard and learn some things on the way. And lucky for us, we also have Dr. Kiyu Liao from the quantitative imaging research team at Data61. So that's a branch of CSIRO. And his team is currently hosting the featured competition, which we will use for all of our examples. I'll give a brief overview of Kaggle in general and the sort of capabilities of it, and then I'll throw to Kiyu for a more deep dive into the competition and the skills required for that. Fantastic. And as I mentioned, feel free to post questions in the chat or just unmute yourself and ask away. Okay, so I'm jumping off at kaggle.com. No surprises there. I'll post links as well in the chat as I go. I'm logged in at the moment, so it's sort of got my dashboard here about things that are happening. So Kaggle fundamentally was was a place to host data science competitions where people could put up interesting data sets and have the community sort of work towards solving something interesting about that data set, usually a machine learning problem where you wanted to predict some future iteration of the data set. And it actually started in Australia and then was bought out by Google. So it's an Australian legacy, which is interesting. And so yeah, the bread and butter of Kaggle really is the competitions, and this is what drives kind of like the engagement on the platform and keeps people, I think, coming back a lot. So at any time there's sort of millions of dollars up for grabs for anyone who's interested in spending a bit of time on a particular problem. And a lot of these are sort of very research related problems. When I was at Sydney Uni, we used Kaggle as a platform internally to kind of create sort of cross pollination between people that may not have the skill set to solve some problems with other people in the university who could, and we had small amounts of money as well put up for that. So that was a lot of fun. So you can definitely use that to solve any research problem, especially if you have the data. It all starts with data. And I think some classic examples on Kaggle, if you haven't used it before, is the Titanic machine learning from disaster. So this is a real classic one if you're just getting started. Teaches you all about machine learning, data science, and tries to predict what sort of features and what parameters for passengers on the Titanic. So if they were a first class guest versus a second or third class guest, if they were a man, if they were a woman, if their cabin was in the front part or the back part of the boat. So all those parameters to see whether they survived or didn't. And so yeah, hopefully that's like an interesting problem, and you might be able to see how that kind of classification problem could translate to so many other things where you just have a whole bunch of sort of predictive variables and then like a target variable that you're trying to understand and see what it is about that target variable that correlates to some other features. So yeah, that's a classic one, but we'll draw our attention elsewhere. So the other, I think, really captivating things for research is that they have so many data sets available. So it's super rich in data. Anyone can upload a data set, and I just have found some interesting examples. If I can spell this right, hyperthyroidism. Yes, hyperthyroidism. So like, any domain or discipline, I just picked this one sort of a bit randomly because I noticed someone used it for a publication recently. And so if you're interested in hypothyroidism, or another example was monkeypox. So if you're researching monkeypox and want to see, you want to pull in more data into your work or something, there's data sets all about monkeypox. You can come and explore the data. You can see, what type of features they have in these data sets. The real classic example is like, standard CSV files, so just comma separated variables with sort of columns of interesting features, and then some column which is the classification target. That's the real classic sort of data set, but you can host any sort of data. You can host audio, and today we're going to be using image data. You can do like videos and other things as well. And yeah, I used to be a geologist once upon a time, so you can just search for things. If you're doing some study and you think, oh, like I've got this data set, but maybe I can add more value if I look something up. There's lots of data sets on all kinds of topics. And so that's, I think, one real powerful part of the platform. The other thing is all the models that it hosts. So any sort of machine learning AI model sort of that has some value, people will put it up here. There are some so there are publishers they're like professional organizations like Google who put up their own they publish their own models on here, so you can get the classic Gemma models and Gemini models, which are sort of our AI models, and then, or our large language models, and then you can go down into sort of more specific use case sort of models, which I guess were much more popular in the machine learning and AI world before sort of large language models burst onto the scene. But there's a whole bunch of different models there. Yeah, you can get the ones from Google. From let's go look at some of Meta's ones as well. So different models, something that will be relevant to your sort of work. So if you're like finding trying to segment the tree roots in a in some CT images or something, like there'll be some model that has done that for you, or if you're trying to find galaxies far away or something, there'll be some model that is already pretty good at doing that kind of thing. But yes, navigating the models and understanding them is really challenging. I'll talk a bit more about that when we go through our notebooks. But yeah, it's very overwhelming and can be confusing. So okay, and like they're probably the main things: competition, data sets, models. There's a few other things. You can check benchmarks if you're into that kind of thing. If you're a computer vision or deep learning researcher in itself, you can use the benchmarks to compare how different models perform. You can also like battle different models and see how they perform. So that's really interesting. Okay, and then the code and discussion. So we will be leveraging code. So we can create our own notebooks, and we can create our own Python notebooks or R notebooks on Kaggle. So we're going to learn how to do that. And you can also go and explore the community's notebooks. So if there is some data set that exists, there is probably a notebook where someone has analyzed it and tried to understand what is in that data. So you can use their workflow, their methodology, and hopefully apply it to your own. And then the community itself, all the discussions, like the richness that comes out of this. When Kiyu and I were preparing for this, yeah, he was sort of very overwhelmed with yeah, how good the community is at discussing and throwing up ideas and talking about things. So there's like general chit chat and forums and everything, but each competition has its own forum as well. So we'll get to that. And yeah, there's like learning pathways, so you can learn how to be a great machine learning engineer or something, and you can become a grand master and compete and go up the rankings. So there's a lot to do. But today we are going to, yeah, we're going to get stuck into it shortly. So we're going to be talking about the Image2Biomass prediction competition, and I'll let Kiyu introduce this completely. I'll just post that link in the chat, and we'll talk through that. So, would you like to? Are there any questions before while you're sharing your screen and setting up? That was a 10,000-foot overview of the Kaggle platform, but as we go through, we'll sort of play with it a lot more. Kiyu, over to you, mate.
Thank you, Nate. And I think not any question for me, and I'll start to share my screen if that's okay.
Please do.
Yeah. Good day, everyone. I'm Ji Liao from CSIRO Data 61's Computer Vision Group, and today I represent the CSIRO Image2Biomass Challenge competition focused to predict the pastoral biomass from top view images. And we have set up this challenge on Kaggle, as you can see from the homepage, to find the innovative solution using computer vision. So let's begin. So the first question, who we are, CSIRO is the Australia's national science agency tackling big challenges across diversity fields. Data 61 is our research and development direction, specialized in AI and cybersecurity. And for this challenge, we are partnering with our 3 key collaborators. One is the MLA, Meat and Livestock Australia, and the second is the Frontier SI, and of course our lovely Kaggle, who's hosting the competition platform. And our team has extensive experience in agricultural computer vision applications, and we have worked on farm environment monitoring and reconstruction, species identification, animal health and welfare monitoring, and red meat supply chain optimization. The Image2Biomass Challenge builds on this expertise. And if you are interested in knowing more about any of these projects, I would like to chat after this section. All right, let me explain why this problem really matters. So firstly, pasture is basically pastoral biomass is basically asking how much feed do I need available for my animals, as the farmer is thinking in this picture. And this question is absolutely fundamental for farmers, and it affects everything, like when to move the herd and how long to let the field recover, and the whole productivity of the pasture. And get it right, and you have got happy, healthy animals, consistent production, and a good soil health. And if you get it wrong, you look at degrade land and wasted feed and stressful livestock. And so how do farmers measure this today? Like there are 3 main approaches, and all have significant drawbacks. The traditional first and traditional one is to clip and weight method to accurate. This is accurate, like we first cut the pasture on the grassland, and then we dry it, and then we weigh it. This is absolutely accurate, but it's incredibly, as you can see, labor costing. And the second is we can use the length of we can use a plate meter to measure the length of the grass. It also needs some kind of correction between the length and the final biomass. And the second is the sensing, remote sensing, using the NDVI. So basically, it's something like a laser device, and it can measure the NDVI value between 0 to 0 means that there's no any biomass on the ground, and if there's a 1, it means much. And it also needs collaboration. And we need something accurate, scalable, and efficient. And here's the exciting part: if you can crack this with computer vision and AI, we could integrate it into the farm management system. Let's imagine the drone and maybe the ground robot or the trucks can automatically collect images and accurately accessing biomass across entire property. You will get detailed information about the total biomass, that biomass, clever biomass, and distribution of those components, and even species of the components, all without manual label. And that's the vision we are working towards with this challenge. So let me show you something about the data set we have put together for this challenge. The input is straightforward. So the input is just the top view RGB image of the pasture taken from above, and all participants of this challenge needs to predict 5 different biomass measurements. Firstly, dry green vegetarian exclude clover. Clover is critical because it can provide more nutrition to our livestock. And the second is the dry dead material. And the third is the dry clover biomass. And then followed with the GDM, which is green dry matter. It equals to the dry green vegetarian and the dry clover biomass. And the final is the total dry biomass. It equals to the first 3. And we have also included some metadata like the sampling day, states, species composition, and NDVR value and the height measurements, which can provide valuable context for building more robust models. And this is a quick show of how our data set compares to some other existing ones in the space. So basically, there are 2 main existing data sets: the Irish grass clover data set and the Denmark grass clover data set. While these are very valuable resources, they're quite limited in scope. Firstly, the Irish data set covers just a single location, and the Denmark covers 2 locations, and they're both collected in a very limited time frame. Like for the Irish one, they only collected from in 3 days, and the Denmark one they collected in a few months, which is not sufficient for a very robust evaluation across the whole year. And our data set has collected more than 1,000 images from 90 sites and across 4 Australian states, and covering the entire year of seasonal variation. So we included, and we also included the depth matters, which is also very important to the final biomass estimation. So I can say that's exactly what we need for practical deployment. And the evaluation will be the weighted R-square metric. You can check it from the homepage. So not all biomass types are weighted equally, because some components are more important than the others for particular farm management. So firstly is the total dry biomass gets the highest weight at 0.5, which is the most important. And we are also keen to know how the components are distributed in the biomass. So here are some potential research topics. Like we can explore into multiple research topics like the transfer learning, few shot learning, because we already released 357 samples for training, and there's a long tail distribution according to the community in some of the biomass components. And we can apply the multimodal learning, image enhancement, and the way we are using the metadata, and maybe we can create some synthetic data. And we will also release some synthetic data and image segmentation annotation afterwards. So really, we are excited to see that what creative approaches from the community can come up with. This is just a starting point, and there's plenty of room for innovation here. And that's all for this data set and this challenge. If you have any question or want to learn more about the challenge or our other agricultural computer vision work, just please feel free to reach out. My email is right here, gel@csiro.eu, and I'm also happy to chat after the session. Thank you for your time, and good luck for anyone participating in this challenge.
Brilliant. Thank you. So it would be super helpful if every competition had an overview like this, but they don't all come with that. So that's really helpful. And you know, we're recording this. Hopefully it'll be sort of shared, and we'll share it in the community as well. And hopefully people will get something out of this. Any questions? Otherwise, I will share my screen again. Let's see. And this one. Okay, so where's the screen? Perfect. Okay, so I'm at the CSIRO Image2Biomass Prediction, and we're going to start coding shortly. I'm just going to talk us through sort of like how you kind of navigate, like where do you start, and obviously, yeah, reading the overview is a fantastic way to go. You know, build models that predict pasture biomass from images, ground truth measurements, and publicly available data sets. So farmers will use these models to determine when and how to graze their livestock. Like, it's a very short, punchy. You know, this is the meaning behind this competition, why we're doing it, and an idea of what's involved. So it started about a month ago, and there's 2 months. So yeah, generally competitions run for about 3 months. $75,000 in awards points, $75,000 plus awards points and medals. Fantastic. And yeah, there's already been 20,000 submissions from 8,000 people. So it's very good. Some of the featured ones are usually quite popular. They have big cash prizes. Some of the smaller ones, they only get 100 entries or something, but they can be interesting too. So yeah, reading the description, it gives you sort of more background. We've just kind of experienced all that. Now, the evaluation, it's something like, I don't think you necessarily have to worry about it too much. Like if you're really down deep in the weeds, then you can start thinking about like how it's evaluated. But if you just sort of build your model and submit it, the evaluation happens in the background, so you don't need to like, I guess, I suppose to win the competition, you know, you got to tune your models to fit that evaluation. But if you're actually just trying to produce a good outcome, then if you're doing science or something, then you can pick 1,000 different evaluation metrics, and you know, they tell slightly different stories. But just know that many different ways to measure, you know, how good of a job you are doing in these machine learning problems. So, or how bad your model is performing, or how good your model is performing. So keep that in mind. And then there's usually a part that talks about the submission file. So this is what basically, this is the file we have to construct at the end of it to submit. And there's some details about what happens. So a lot of people work in teams. You know, they work together. They share their code, and they can pool their submissions and things like that. So teamwork is a good thing. And what else is it? Oh yeah, so important things that might come up. They usually have like rules in the competition around how long a task can run. So your notebook you submit has to run less than 9 hours. So that means you can't necessarily train like really expensive models whilst you're submitting it. For this competition, your notebook can't call the internet. So we'll see where that might affect us. But you can grab data from anywhere else as well. So So some competitions may not allow that for different reasons. This one, they want you to. And yeah, there's the prize breakdown and the acknowledgements. So that's kind of like the overview, and all overviews kind of look like this to give you an idea. The next thing, when you're starting to think like, okay, how do I approach this problem, is the data tab. So the data tab explains, exactly what you need to do. So in this competition, your task is to use pasture images to predict 5 key biomass components critical for grazing and feed management. And so they're the 5 targets that we are trying to predict. So accurately predicting these quantities will help farmers and researchers monitor pasture growth, so on. And so this describes our the data. So what files are provided. So there's a file called test.csv, and we'll see all this in action momentarily. I know we're all excited to get there. So there's a CSV file that contains these headings. There's a training directory that contains just the JPEG images. Oh yeah, and it also says here the test set contains over 800 images. And so there's a test directory as well. So this directory is reserved for the test images. And most of those are hidden from people, from participants, except when you submit your notebook to get scored properly. And that's just so, you can't just game the solution, hand code everything. You actually have to do genuine work. Your notebook has to be predicting on unseen images, because people want these models to be useful in the future, and CSIRO wants to be able to take these models and use them in the real world. All right, so and then there's a train.csv as well. So there's a CSV file that has all our training information and a couple extra metadata bits that aren't in the test set, and sample submission and the submission file. Okay, so and you can even browse sort of the data. You can browse it down here. You can do this for all data sets and all competitions as well. And you can explore sort of what's in there already. You can look at it in a few different formats. So you can get the information about the data without actually downloading it or opening it up fully or anything. You can look in the test set and see that there's only one image in the test set we can see, but there's those hundreds in the actual one, and there's all the training images as well, and then just JPEGs. Now up the top, okay, we'll talk about I'll talk about, does the test set also have metadata like height, etc.? Great question already. So no, it's not in the test set, and I don't know how. So in the examples that I'm going to show, we won't use the metadata. We'll look at it a little bit, but I'm sure there are intelligent ways you could use the metadata to do some kind of more intelligent feature engineering around how you train and predict and build your model. But short answer is no, it's not in there, which is interesting, and something that I think people found out. So on the code tab, this is all the notebooks that people have submitted. Oh, sorry, was there another question? Good. These are all the notebooks that people have submitted, so that there's hundreds or something. So these are all the public ones. You don't have to share your work, but a lot of people do, and so that's super helpful. You can search for them by who got the highest score in the public notebooks. I definitely did not, but yeah, you can see the top public scores down here. So 0.65 seems to be the highest public notebook. You can see which ones are maybe the most interesting by what's been upvoted, and hotness. I guess they're maybe recently changed ones. Oh yeah, there's our one that we'll be using, and you can also see. So out of the thousands of models on Kaggle, you can see which models are being used in this competition. So that can give you maybe a head start. If you're joining a bit later, you can see which ones are what people are using. So there's not that many models that people are using. We'll be using EfficientNet today. I guess there's a few different variations of this EfficientNet model, and other people are using Dino. Actually, most people are using this Dino model. So that's interesting, you know, something to think about. And just bringing it back to sort of like research work, you know, if you sort of don't know where to start, you can find a data set, you can find a competition which might be closely aligned to what you're trying to do, and then you can see not just the method that people have used, but like what kind of models people are using to explore it, so you can get a good idea for where to start. Okay, and then the discussion, there's lots of chats on here about problems that people are having. So it's real community driven. Everyone's super friendly. You know, there's no silly questions or anything. And the leaderboard. So this is what it's all about in the competition phase. So this person, Orion, is currently winning with a score of 0.75, and this is only. So it says here, this is calculated on 53% of the test data, and they only do it on all the data when they close the competition. So that keeps like it interesting. So you often find that people's models, they might be highly tuned to just the test images that are available during the public part of the scoring. So if you want to build a generalized model that can work well in more scenarios, it needs to kind of perform when you get new data. So that's why you sort of keep a lot of the data sort of hidden from people. And my name's somewhere well down here. There we go. When I published this, I got a score of 0.45. I think I was like 30th, but that was like on day 2 of the competition. So I've slowly dropped down the rankings. Okay, and then there's typical rules. Oh yes, so I've accepted the rules for this competition. Up the top here, there's probably a button that says join competition. Please click that if you haven't, and I'll just talk about briefly. So if I go to my settings, for this competition, you need your identity verified. So you basically have to you just have to put your face on screen and point it around. It seems fine, and you also have to have phone verification if you want to use GPUs and accelerated computing at all. So these 2 things which sort of are a little bit extra for this competition. Some competitions, you don't need to do either of those things, but for this one you do. Okay, so let's go here, and we're going to start coding. So I'll just search for GDG there. I'll post this in the chat. We're going to start with this this first one, and I'll open it up. I think it's already open. I'm going to be following this along, but I'm actually going to start a new notebook. So let's put it in the chat. So you can either click on here. I think there's a button which will be copy and edit notebook, or you can fork it or something. It might be different because I own this one already, but you can get started. However, I'm going to start from scratch. So I'm going to click new notebook back on the code page. And we're going to be running through this notebook, and I'll mention everything that we do in here. Basically, we're going to load in the data. We're going to do some EDA, some exploratory data analysis, and sort of understand the data. Then we'll build a model that will help us predict unseen images, and then we apply the model to the test images. And again, in your research, like basically everything starts like this. You get your data, you wrangle it, you do some EDA, and then you then do whatever you need to do with that data. Okay, so I'll go back to my new notebook. Oh, let me try again. code, new notebook. Okay, good stuff. And so it's automatically, yeah, so it drops you in this this format here where you it gives you sort of some starting code basically, and you can immediately just run that code, and what it does, it prints out all the files that are available to you at this moment. So this is running on a virtual machine somewhere. It's a Docker image that you're inside of, and you can add sort of data sets and models into that Docker virtual machine. You don't need to know any of that, but just so you kind of know what's under the hood. All right, so my session has started. And you can see, because I clicked new notebook on that particular competition, it's automatically like put the data that we're going to need straight in there. So it's a whole bunch of JPEG files that are on the local file system. And so I have direct access to those files and can use them. All right, let me sort of hide that. And that is indicated over here with the the competitions. And we're going to add more models to this panel as well as we go along. You can also upload data, and it shows you what's in your output folder. We have nothing in there at the moment, but yeah, you can browse around the data sets there. I think you can even really look at them. Maybe you can download them. Oh yeah, so there's some grass, first grass image, fantastic. You can look at the CSV files. So they're down there as well. But we're going to load all this in and keep exploring. And so you can also copy the path, the file path. So this will come in handy as we go. Let me hide this stuff. But it's basically, yeah, this file path. So, all right, all right, I'm going to delete all this and start from scratch. I'm going to go import pandas as PD. So to begin with, we're going to do some just loading in our data. And generally what we want to do is set up our base path. So that's where like all our competition data is. You'd probably do this if you're working where, you know, on your local machine or something as well. Just good standard coding practice. Okay, is everyone with me? Does anyone need a moment? You can definitely get access to the recording after this, yes. Okay. Okay, oh yeah, and so I just loaded pandas. I didn't have to do anything. There's a whole bunch of like Python packages and yeah, different Python packages that are useful for the kind of work that gets done on Kaggle. You can install stuff if you do need something that isn't available, but in general, like I rarely come across something that isn't there. Okay, and so we've got a base path. We also want to load in our training CSV file. So CSV is going to equal the base path plus train.csv. Now, these are all, the paths are all here. I'm copying off the full sheet so I know where they are. And if you do any competition, this is normally approximately what it looks like. So base path plus test.csv. So that's our training CSV, our testing CSV, and we'll read it in immediately. Train, so df train equals pandas.read CSV, and then the name of our file. Okay, and then we'll also read in our testing set, read CSV test CSV underscore path, and then we can just print them to the screen, basically. Display the train, display the test. Let's see if we got our data. So I'm just pressing Shift Enter to run this cell, but yeah, let me know if anyone's not familiar with the notebook. But basically, it's Python, and you just click play, or you can press Shift Enter to execute that cell, and it runs that Python code. And yeah, we get an overview of the data here. So this is, you know, really good to understand. As much as, you know, it's written down and described, it's good to actually like see the data ourselves and use it and play with it. And so we can see the first training.csv. It's a CSV file that has 1,785 rows. So it's basically 5 rows per image, because there's 5 different classes that we're trying to predict. So you can see, yeah, dry clover, dry dead, dry green, dry total, all for the same image, and image ID. And then it has this metadata, sampling date, the state, the species, the NDVI, and the height. And then it has the target name, which is kind of written in the sample ID as well. And then the target. And so this is an amount of the amount of this target in grams. So the first image has 0 grams of clover, almost 32 grams of dry dead, and 16 of dry green, and 48 of dry total, and 16 of GDM, green dry mass. Okay, so yeah, that's what the training data looks like, and the test set is it's very sparse for this competition. This data set is just 1 image in the test set. However, as we'll learn, when we submit our file to get a score, what it does is it basically removes the current test.csv and test folder, and it replaces it with the hidden stuff. And so then it will test on everything. So you need to write your code in kind of a general way that will be that it can just you can sub out different files, or a different file called test.csv. But yes, importantly, in the test data, there is none of the metadata there. So yeah, we can think about what that means. All right, so let's, the first few statements again. Yep, so import pandas as PD, and then the base path, train, test. And yeah, they are all in the, just posted in the, maybe it's all in that notebook as well. So I'm basically following that notebook. I have it open on another tab. I'm not writing this all down from scratch. Cool. So okay, so now what we're going to do is just you know, we want to look at our data a bit more, visualize it, understand it. This is again normally where you start for any sort of data science problem, and there's quite a few ways to do it. Let's get a sample row out. So sample rows equals df underscore train, and then sample. Can use this. We'll get out 5 because that's sort of done in the notes. And all this does is pulls out basically 5 random rows of our data set. And so we'll play around with them and see what they are and what's in them. So we can make a plot. I haven't imported my plotting stuff yet, so I might just do that. I did it at the top in my other notebook, but we now need to use it. So all these import, sorry, matplotlib as dot matplotlib.py plot as plt. We're going to import cborn as SNS, and we're going to import this package called pill. From pill, we're going to import image. And this is literally, we're only using it in this case for actually visualizing the data. Okay, so then to view an image, you can grab the full path of an image equals the base path plus one of these sample IDs. So I'm just sample rows. I'm going to modify this code in a second. Sample rows, let's just do .iloc0. Well, that might not work. And let's go, or did I do this wrong? I think I did. Sample rows. I want sample, oh, sorry, I want image path. Image path, which will be that path. Okay, so I just want to get that full path. Let me just print it out so I make sure it's right. It'll work. Cool. So it's going to look for a file there, and then we can load it in and have a look at what it does. So I can use this package called image.open. Image, sorry, I'll try and not make typos. Image.open full path. And we can do plot.imshow image. We just want to get an image up. There we go. Good stuff. There's some graphs. So we'll yeah, we're going to visualize this and just make it look pretty, so we get an idea of what the grasses are. We'll have a look at a different one. It's this one. Oh yeah, so there's another one. You can browse through. Cool. So there's all our graphs. Now I might just copy and paste from here just to get the full code to make it look nice, because there's nothing fancy in here. We load in the image and we plot it. There's just a bit of trickery to make it plot nicely and add some text on there. Close that one, open that one. Okay, let's do that. And then we run it. Look at this. So, oh yeah, they're actually, I've made them way too small. Let me make this bigger. I'll do, let's go 2. I'll just do 2. You might have more real estate on your screen. Okay, still very small. I'm going to increase my font size as well so everyone can see. You don't have to do this. Cool. So yeah, just again, they're just sort of random images just to get a visual concept of what we're actually trying to do and what data we have at the moment. So we have our sample IDs. We've got the date and the state. That could be interesting. I'm not sure. Maybe you can think of ways to use that information to your advantage. But the species that is in here, and then the NDVI, the height, and then the target name and the mass of stuff in there. And yeah, so in this image, when looking for the green dry mass, there is 58 grams of green dry mass. But there is, and in this image, there is 0 grams of dry clover. So, but then there'd be the other targets would probably have some amount in there. Very good. So that's our images. Any questions about that? Because we can also explore our metadata. So I'm going to use Seaborn here. So sns.scatterplot. I'm just going to make a scatterplot of the data. So the data we want is the training data set. We can set the x-axis to this column. You can pick any of these columns really. So we can go height, average centimeters. Great. And the y-axis, we will go the NDVI component. Fantastic. And then the hue, we can make the target name. So that way we target name, great. Okay, so let me plot that. That work? Oh wait, sorry. So that's X, that's Y, and why are they all purple? They shouldn't. Oh, it's because I need alpha equals 0.5. Okay, so then we'll be able to. Is that all right? No, I'm doing something wrong here. Data df trained. Maybe the Y should be the. Oh, okay. The hue. Sorry, this should be target, because of course so the Y should always be the target. So that's the amount in biomass. Yeah, so that's the biomass of the target and they're colored by what group they're in. And there's the height. And if there's a really strong if there was a strong correlation between this metadata component and the target, you'd see sort of distinct clusters. And yeah, I think that's about right, Angus. So yeah, the red stuff up here is the dry total, and it seems to weigh more in total than the clover down here, which is shorter and doesn't weigh as much or something. So yeah, there's some takeaways there. You can keep exploring this. So let me plot the NDVI this time. There's 1,000 ways to sort of explore the data. This is just kind of experimenting with what it looks like. This one seems a little bit more random, maybe yeah, lots of red dry total mass up high, something in that. Anyway, so that's just getting a sense of the data and what it looks like and potentially what we can do with it. For now, we're going to do a really simplistic approach. So this notebook only basically has two more lines to it, and then we'll take a short break, and then we'll come back and go through the advanced stuff. So what we do next is implement our strategy. We've thought long and hard about this data set, like what are we going to do? And a great way to start in Kaggle competitions and probably with your own data as well is just get a baseline sense of what's a good value to what's a reasonable amount. Like I have no idea, how much biomass there should be in these things. So what we're going to do is basically take an average of all the training data and just apply that average to all the test data, and that will give us a baseline. So if it's kind of like just throwing randomness at the solution and seeing how well we perform in a random baseline. Although this, because we've got a specific target with a real world value of a mass, yeah, random would be very random. Okay, so let's go target by name equals df train and group by oops, and right, okay, group by target name and target, and I'm going to take a mean and reset the index. Okay, so this is literally just getting the mean of the training data, and we're going to apply that. So that's our baseline. That's what we're going to predict every single test images forevermore. CSIRO is going to be like, yes, you've solved the problem. We just take the average of the training set, and we know approximately how much grass is going to be in there. And that's not a reasonable assumption that's somewhere to start from. Okay, so then we apply it to our model or apply it to our test set. So submission equals df test dot merge. So these are standard pandas functions if you're not familiar with them. Target by name. So we're going to merge this data by the target name, and how equals left. So we're taking our test set, which is back up here, and this could be thousands of rows long. And we look for the target name. So any target names, which is this, we're going to give the value of the of that. That's all we're doing there. And we only want the columns sample ID and the target. So some pandas trickery, but that's basically it. And then we'll display it. Okay. So yeah, we've just modified this little data set that we've made. And this would work for any test.csv file that we threw at it that had those that had that same structure. So that's why we need to do that. And that's the framework. So we load our model in, we run some, in this case, a very simple metric to come up with a model, but it could be super advanced. It could be thousands of lines long. But then at the end, we need to come back and we need to apply it to our actual test.csv. And so we apply it. And then finally, we have to create a submission file. So some competitions, you actually, you just submit the submission file. You don't have to submit the code. And it has to be in submission.csv. And important, we get rid of the index false. So index equals false means it won't print out those numbers as well when you save it. Cool. So I run that. And then up here, I should be able to see, can I refresh this? Where's my refresh button? It's hidden a little bit there. Okay, refresh. Ah, look at that. So there's my CSV file ready to go. And now I'm going to click submit to a competition in a second because we've got our notebook. We're happy with it. We've created a CSV file. And let me check my session options. So by default, the internet is on. I know that I need to turn that off in order for this to pass. If you try and submit it, it will be like, actually, maybe it won't. It just won't have internet on the, it won't have internet when you go to the, when it runs in the thing. So that's probably fine. But if you've called the internet at all, it'll just fail. So we're not using a GPU or anything at the moment. We're using Python. We could have used R. The persistence, that's about saving our data. Don't need to worry about that. And the environment in the future, if you run this again, it might be a different pandas version. It might be a different plotting version. So keep that in mind. So that's why it's pinned to the original, but you can modify that. Cool. So I'm going to click submit, and let's see how we go. Hopefully everyone gets a score. All right, so that should take a few minutes. Let's take a 5-minute break, and hopefully when we come back, that will be finished. It should only take a little bit of time. So I think that there's some things happening in the background. You can click on the diagnostics and see what's happening in the logbook. So it's running in the background. You can read it all. Hopefully it'll work. But anyway, we'll have a look at this in 5 minutes time. Back, everybody. So let's see how our notebook went. Successful, fantastic. So that's good, it completed. And where's my score? Did it work? Complete, successful. Should give me a score somewhere. Yeah, there we go, 0.25. So great job. Hopefully you got a score. You got your first Kaggle competition. I find that really like nervous, you know, you don't want to get a bad score. If I scroll down, you can see, look, some of my first scores were like -1.2, and I'm like, how do I get negative? so you know, getting the baseline up is very good, a great start. There, -10, it went down very, very hard there. Just trying different approaches, seeing what works. So hopefully you got a score, and from there you can build. Once you've got that framework right, you can see here I dropped off and just kept failing for a bit. I'm like, why is it failing all the time? And so I actually went back to the discussion board, and on there found the solution that I was I was doing something that caused it to fail each time. Anyway, so yeah, any questions? Anyone get better or worse than that amount? Let's go to a new notebook then. So now we have a framework. I'm just going to just remove sort of all the stuff we don't need, just to show you how sort of compact this workflow actually is. So delete that, delete that, delete that. It's literally, we can do it all in, let's keep that, whoops. Okay, so it's literally 1, 5, 6, 7, 8, 9 lines of code, you know, you can submit to the competition. So you import the package, you read in the data, you apply some model. In this case, it was easy, and then you merge it back with the final the final target data set and create the submission file. I think that's so cool. So, but there you go. Then you can plug and play that that framework for anything, and that's what we're kind of going to do. So I will go back here. Where do I have it open? I do have it open. I have this other notebook, which we're now going to explore. This one, I might have some more copying and pasting because it's a fair bit more involved. Basically, in this notebook, we just sort of revisiting the problem. I always like to think, like, what are we actually doing? Because the approaches that I was using that like absolutely didn't work were like classic. I was just trying to detect what is this image, what is in the image here, like where is the grass, and do like image segmentation, and that was just failing miserably. But a much better approach, and I think the most of the winning or really good codes that are on the public leaderboard are using this sort of feature that they use a model to predict, or sorry, they use a model to extract like higher dimensional features from the images that humans, you know, can't comprehend, or maybe we can comprehend, and then rather than trying to predict, you know, what's in that picture, you then use those features to train another model on top of it, and use that to then make a prediction. So yeah, so explaining that more simply, we're tackling a multi-output regression problem. So we aren't predicting one thing like grass or no grass. We're predicting 5 different numerical continuous values. So they're 5 different biomass components that we're predicting. So for each one, yeah, it's a continuous number, so it's a regression problem, and it's not categorical like a binary yes or no thing. And so in this notebook, the more advanced one, we're going to use a pre-trained model to extract these high dimensional features from each image. So they'll be, you can kind of think of them as things like the greenness, the shapes that are in there, the shadows, the contrast, the brightness. You can think of them like that. It's not exactly like that, but you can think of them like that. They're features that the computer vision is able to detect. And then from there, we build this massive feature vector, and we're going to build then a classical machine learning classifier, or a typical clean machine learning classifier trained on those parameters. So, and we're going to use a model called EfficientNet, or EfficientNet version 2, which extracts the key features or attributes, color, height, shape, etc. in the images. And then we're going to try and train 5 random forest machine learning models. So that's the 5 models are basically 1 per class. So each of those things are treated independently. And then we're going to predict those 5 classes. And so this notebook's okay, like a score of 0.45. The highest is 0.75. But this is very, again, you know, you can do a lot better things, I think, and that's what the winning notebooks are doing. But I wanted to do something that was, I guess, simple. So, okay. And yeah, important to point out, like Kaggle datasets, they can be really messy. So I've got like no defensive programming in there, no try except statements. I haven't cleaned up any nans or anything, or images that are missing. Sometimes images are missing or corrupted or something. So just keep that in mind when you do. If your code is failing for some reason, it could be that the test data is actually pretty different to the training data. In this case, it's all good. So okay, I'll go new notebook, but I will sort of be copying and pasting between the two a little bit. So let me go to my, what's the code? There we go. Wait, new notebook. Sorry. Let me go here. Let's start from there. Okay. Code, new notebook. I just want to show you how to do some things. Can I toggle hide sidebar? Cool. I'll hide that for now, just to give myself a bit more screen real estate. Once again, you can see that it starts with this boilerplate code just to get you sort of in the right area, the right. People in public notebooks seem to really like defining classes to manage their models. Yeah. So some of the code in the notebook, the public notebooks, what I've literally been doing is copying them into Gemini and be like, can you explain like what this person is doing? And it does a really good job. So it dumbs it down for me and makes it understandable. But yeah, there's a lot of classes which are a relatively advanced Python thing. So, and I've avoided using classes in this workflow. Okay, so what we're going to do, I'm going to delete all that boilerplate code. We're in the same data set. It's 2:20, so I've got about half an hour or so to get through this. As I said, I'll do a fair bit of copying pasting, but I'm going to import some things. So I'm going to import OS. I'm going to import pandas. Import pandas as PD. I'm going to import numpy. So numpy as np, and I'm going to also import this library called tqdm, and that's literally just a fun little library that that's useful for timing things. I don't know what it stands for, but yeah, it just helps you time your code, so you have an idea of how long it's going to take. And then for our machine learning, we're going to be using scikit-learn, which is the real classic and standard machine learning package. And from there, we're specifically going to be using an ensemble model called random forest regressor, I believe. Let's see, import random forest with 1 R, regressor with 2 S's. Cool. And we're also going to import TensorFlow as TF. So I'll run that. And you might be going, you don't have a GPU. You're correct, but that's okay. We'll get to that in a second. Okay, so I'm getting a bunch of warnings up here. It's probably fine. That one's an error, but it's probably fine. We'll see if this comes back bite us. I mentioned, yeah, that there's different, different libraries and everything in the Kaggle platform. So they're constantly like updating things, and they're probably suffering the same thing that people do when they update one package and other things don't work, or they might work a little bit. So I think that's all good though. I'll run it again and maybe those errors will disappear. There we go, perfect. So problem solved. Okay, so as before, we'll do the base path equals that Kaggle /Kaggle /import /CSIRO biomass, because I can see, yep, it's there. You can also copy that out and paste it in. So you can just copy it there. Hide that. Okay, and like before, we're going to use the train.csv and test.csv. Same, exactly the same as before. You can probably even fork your own notebook if you wanted to. And in fact, yes, I'll copy. I should copy from this one. Sorry. So I'll just copy the train and test, and then I might write that next bit of code. Okay, so I read those in. We can check them like before. Perfect. Our data is the same. Now this time, what we're going to do is we need to we're basically going to drop all the metadata. I know we've spoken about it, but like I'm not a good enough deep learner machine learning engineer to think about what I could do with this, use it for. So I'm just going to drop it, and we're just going to keep sort of the targets and also the target names, and we'll get rid of kind of everything else and go from there. So we're going to create a wide format data frame. So if you've ever used a pivot table in Microsoft Excel, hopefully we'll see what that looks like in a second. So the index is the image path. So this column will be our any duplicates in here will become a single value, and the columns that we're pivoting on are the target name, and the values that we're keeping are the target. Okay, and yeah, let's reset the index so we keep pandas happy. Okay, let me just display our training data frame, and then display the new data frame that we've just created, just so we can see what it looks like. Okay, so there's our original data frame, and this is what the pivoted one looks like. It's literally the image path. There's only one per image now, but for each of them, we have 5 target classes. So there's probably different things that we could do this. Other species in the test data set constrained to be a subset of the species in the training data set? I don't actually know. So Chiu, are you online? Maybe you know the answer to what the species are and how to use them and everything. That's something that I haven't thought too much about. But yeah, they change per, I think it could be like the main species for that particular image or something.
Yeah, the main species should be the same, and at least the top 3. It's technically impossible to list all the species in the picture, and some of it we don't know, but it must be minority. For the majority, they're aligned.
Good stuff. Okay. All right. So now in the advanced notebook over here, I now have a model path. So what we're going to do is load this model in. There's a couple ways to do that. In your side panel, keep turning mine off. The easiest way to do it is if you look up here and click Add Input. And you click Add Input, and then it's got all these options. Those are the things that I've looked up recently. I'm just going to select Models, and I'm going to type in efficient net oh, of course I spelled it wrong, efficient net V2. Oh, and my thing's just a bit small, so I can't see the icons. Hopefully you can see the icons though. But we're going to use Keras as a framework. So it might be worth just talking about that for a second. So before I add it in, I'll just go back to maybe the main, do I have the main page? Let's go to kaggle.com. In models, so if I look up efficient net here, you can see, yeah, it's grouped by like organization models. You know, they're normally powerful, but then people upload their own versions or whatever. So there's 113 of them, and then it also plugs into the Hugging Face. So if you're familiar with the Hugging Face platform, you can also grab models directly from there. But we are looking for the Keras one because we're going to use that one, EfficientNet V2. And when you click on this is what's called a model card, and it describes kind of like what the model is. And like how it was built, and links off to different places, how to use it. And then it has like all these different variations of the model as well. And it can be so overwhelming to be like, which model do I use? So, and I don't know the answer to that. It's sometimes the model, it's somewhat clear. So in this case, I think B0 is the smallest one, and then they get bigger down to B, I think it goes up to B5 actually. But we're actually going to use the S version, which is an even bigger one. And then down here, you can select the variation of the model. So this is where you actually select it, and you can explore them. But if I just go back as well, so there's different frameworks. So EfficientNet V2 comes in lots of different frameworks. So if I click on like the Google one instead of the Keras one, and I go down to here, you can see that it's got TensorFlow. I'm looking for, if I go to there's a TensorFlow version. Oh, that's the original EfficientNet. Oh yeah, there's a few different frameworks you can pick from. So TensorFlow 2, LiteRT, and TensorFlow 1. So, and the different frameworks are basically different Python packages that read the data in slightly different formats. And so people have just loaded the data into one framework, rejigged it, and saved it out in the other format. So it just saves a lot of time and energy. Okay. So anyway, that's a small digression into how to pick a model, what models are available. You can download the models. You can start a new notebook with the model directly from there as well. But I'll go back to Kaggle. Sorry, to my notebook that we're editing, and I'll click that little plus button, and then it says, oh yeah, which framework do you want for this version? Because Keras has published this one. The only option is Keras, but often there might be different frameworks like PyTorch or TensorFlow or Keras or something else. And then there's the variation. And so for this, we're going to use the EfficientNet V2S ImageNet classifier. So, and the version, I guess there might have been a bug in the first version or something, so they released the second version. Great. Has everyone got that? Clear as mud. So I'll click Add Model, and it will import it into our workspace. Cool. So there it is. It has this little icon. It's got different data in there, and if I just copy that, I can see that it's in. Let me just hide that. Hide sidebar. I can see that it's in Kaggle input EfficientNet, Keras EfficientNet V2 classifier, etc., etc. I can actually just do some simple Linux commands here and print it out. So in there is those 3 files, and so it's given us the sort of the model architecture, and then it's given us the model weights as well. So sometimes you may not want both. You might just want one or the other. Great. So now we have access to this thing. I'm going to say model path equals, and that's the path of the model. So when we load it in later, we can use that. And I'm going to set a couple of other things. The image size. So at the moment, our images are landscape. They're 2,000 pixels by 1,000 pixels, and that is a thing. Definitely the best notebooks on the competition on the leaderboard, they take that into account. So these computer vision models, they've been trained usually on small images. Maybe, so this one I think is 512 by 512 pixels, so that's relatively small. And as GPUs are getting more powerful and that you can store like a full image on a GPU, then hopefully we'll see that explode a bit, or that grow. But for now, I think this is one of the real shortcomings of this approach that I'm talking about now, is that we compress the model down and we lose all the fine grain details of like a blade of grass, because we're compressing it down to 512 pixels and we're squashing it as well. So if we cut it up and did it a bit more intelligently, we'd probably get a better score, but that's okay. All right, what's next? So we set that, and so what we're going to do is build this thing called the feature extractor. We're going to use this model as a feature extractor. So when we Efficient2, they've all got fancy names, but they're all basically different like architectures of a convolutional neural network. So they all have like a different. They all usually start as some tensor representation of an image, or which might be, you know, like the x coordinates, the y coordinates, and plus like the red, green, and blue values. So it's like a tensor, and then there's some mathematical transformation which would pull out some features of that, and then another mathematical transformation, and then another mathematical transformation, and you keep doing this, and that describes the architecture of the neural network. And then eventually it comes out, and at the other end, you know, you have this. You start with this tensor, and at the other end is the word dog or the word cat or some classifier or something. And so there's all these mathematical transformations which can lead you to the answer: dog, cat, or grass in this case, massive grass. And so this original model was trained on lots of images, but we don't care about the images. We care about the knowledge that it sort of grew and understood to learn what an image is. So it doesn't know immediately, you know, that's a cat, that's a dog, that's a car. It just knows it has all these values associated. Oh yeah, the light, the shading is like this. There's a sharp line there. There's a contrast over here. Like it's got all this structure of an image in its mind, and then it goes, therefore it must be a dog. So we're going to cut off the last bit where it says, therefore it must be a dog, and just capture all that knowledge about any particular image that it learns beforehand. Hopefully that makes sense. So yeah, we want the feature-rich internal description generated right before it makes that final decision. So it knows what edges, textures, shadows, shapes, etc. look like in a somewhat abstract sense, and we'll use those understanding to build our own classifier for graphs. So the way we do that, I'm just aware of time, and I like to talk a lot. So the way we do that is we load the model in, and Keras sort of abstracts so many details from us. Keras is like wonderful and makes things easy compared to TensorFlow, PyTorch, but it does remove a lot of the knobs to tweak, I guess. But we load it in. We basically say, give us the second last layer, the one that had figured out all those features, but before you turn it into a picture of a dog or something, and just give us all the mathematical representation up to that point. And we're not going to fine tune in this or anything. So we freeze the weights. So this Efficient2 has also been trained on a huge class of images called ImageNet. And so a model is basically two parts. It's the architecture itself, which I think is the backbone, plus the weights. So the architecture of the model is one thing, and then the weights that it's learnt to predict is the other thing. And we're using both, but we don't want to modify them. So that's it. We load in the model, we cut off the end, and then I think we're good to go. So let me copy this. and put it in here. So I'll run that. Got our model. Hopefully that loads. Whilst that's loading, I'll look at the next bit. Okay, now we're going to define a function that reads in our images and actually does all the stuff that I'd said. So all we've done is load in our model, but now we are going to define this function that actually, all it really does is load in the image here. So it sets the path of the image, loads in the image, converts it into a numpy array as opposed to whatever PIL format it was in originally, and then it applies the it pre-processes the image. So you need to scale it, the pixels, and get the image into the right, I guess, format exactly for what EfficientNet expects. And again, Keras does all the heavy lifting for us there. This is a Keras application here specifically for EfficientNet. Keras has a bunch of models that it's like got functions for. And then finally, we use the Keras predict function to then give us the answer. So going through that neural network, all the steps, all those mathematical transformations, we put our image at the top, we run it through the prediction pipeline, and it goes through, and then at the end, it comes out with that set of features that we're going to see. Hopefully that's clear. So hopefully it will be when we run anyway. Okay, model loaded, great. We don't have CUDA because I don't have a GPU. I'll come to that. 20 minutes, good. Okay, so that's just a function, so that ran straight away. Okay, so here's the hard part, and this is probably where it's going to fall down. Now we actually just apply that function that we've defined to every single image. So it's got to go through the hundreds of images and run through that function. So it we grab the path file name of the image, and we run our extract deep features function on all of them, and we put it into a data frame, the features that come out. So let's see, that's probably going to take forever. So maybe I'll cancel it. Oh, how long? Oh yeah, no, that's reasonable. I'll cancel it anyway. So I'm going to get myself a GPU. If you haven't phone verified your account, you might not be able to do this. But basically, I can go up here, click accelerator, and pick a GPU. So I'm going to turn on my GPU. I could have also done it from the sidebar over there. So down here, the session options, there's a GPU. It does sort of restart my session though. So let me hide the sidebar. And so I have to do everything again, but hopefully it should be quick. I'll just run through it all again. And this time it should only take about a minute to run once it starts. Okay, and when it gets going, what's next? Any questions? Oh yeah, sorry. So do we need to consider the plant disease feature? Oh yes, probably is the answer. Yeah. So, I'll save a bit of time just to explore some of the notebooks on the leaderboard, and we'll see, yeah, what advanced things that they do. Okay, so my session has started. Good. I got those errors again. Fantastic, but it's still working. There we go. My model's loading. So it's putting it onto the GPU. And okay, and now it's running. Oh, look at that! So much faster on a GPU. There you go. Tell your universities to buy you some fancy GPUs to do this. Okay. So while that's thinking, that'll take about a minute. I'll go down here. It should print out our CSV file, which will be all those features. In EfficientNet, there are 1,280 features, these abstract features that it pulls out, these mathematical representations of the image. And basically what we're going to do is then use those features to predict our biomass targets. And these could be things like in the real world, these could be things like NDVI, like the height of the picture, like the greenness of it. So things that you might actually be real, but they're not. They're just sort of more, yeah, mathematical constructs. Okay. But anyway, we'll still use them because the machine doesn't care, you know, what they are or what they aren't. It just it's going to be happy to take them. Okay, so then we then set our target columns. There, our target columns, the different names. So the first 5 things in there are all individual targets, and then the next are all features. So that's all we do there. We split our data into our training set and our target set. Okay. So I'll copy and paste that one. And yep, we can see we've got our targets here. We're really doing 5 different tasks here. Again, probably better ways to do it is to think about them all together. I think there's actually, people figured out that there's like just a real relationship between some of these variables. So like the total is just the sum of these other ones. And so that sort of saves your training and makes it like much more real, I suppose. Okay, we can plot some things. I'll just talk through these plots, so I won't plot them myself. But to give you an idea of, you know, what these features mean, so I think I've just pulled out like 2 random features. If they were really great features that separated the clusters of mass, we'd expect to see, yeah, all the yellow stuff like up here or something, all the purple stuff down here, which is just the overall mass that we're predicting. And another way to look at it is, so it pulls out the 1200 features or so. I've plotted the top most correlated features with one of the particular targets and the most negatively correlated, but these trend, you know, all the way through 0. So there's a very long tail of features that aren't so important and features that are more important in separating and making predictions. Okay. Oh, and this is a nice plot. Maybe I'll do this one. So this, let me copy this one here. Okay. So in this one, we're going to actually just visualize all those features and what they mean. So for this particular patch of grass, this is what that representation looks like. So somewhere in the convolutional neural network, it has reached this point where it has these 1200 features. And for this particular piece of grass, this is what those features look like. Compared with this piece of grass, this is what those features look like. And so these are the numbers that we're now going to give to a traditional machine learning model to learn from, to try and understand what's in there. But yeah, keep in mind we've squashed and compressed these images, so it might not be as perfect as we want it to be. Okay, I think, yeah, that's a cool way to look at things. Now, where are we up to? So now this is where we actually train a model. So we've used a pre-trained model to sort of build our feature set, which worked well. Now we're going to use a random forest regressor on each of our each of our targets. So we're going to loop through the 5 different biomass targets, and for each one we're going to build 5 different random forest models and fit them between our Y targets and our X training set, which is basically these 1200 features get trained on that first column, and then they get trained on the second column, and then third, and then fourth, and then fifth. And what they should produce, so that doesn't take too long. I think that's just using CPU. It's pretty efficient. You could sub this out for like a better model, maybe some ensemble model to do a better job. But I think the random forest is simple for now. And yes, okay, also pointing out, coming back to the idea of Kaggle, at this point, like all we've done is train our model and it's ready to go and ready to make predictions now. If that takes a really long time for whatever reason, it might be you might have a big data set, you might have really long training runs or something, then you can actually just save that out. You can save that your model out and then you can create a new notebook and load that model back in, and you'd save a lot of time. And then you submit the second part of it. So that's one thing you can do to sort of speed things up, because all of that took a long time. Well, for us, it only took a couple of minutes of actual computational time. But if it was a different problem, it may take, over the limit of whatever the competition allows. So we can save that out. So the next thing we do, just like we did before, where we applied our predictions in our very simple notebook, we're going to do the same thing here. So we predict. We take our for each of the test image, we pull out our we use our extract deep features model to function to pull out all the features that we want to test our model against. So then we have a data frame of just features, and we want to see just features from our image, and we want to predict something that we don't have the answer to, like we did before. So I'll copy that. Okay. And there we go. So at the end, in the test set, there is actually only one test image. But once it gets submitted to the competition, then there's then there's sort of hundreds there. But yeah, like that's our predictions. I haven't done any validation here. I think I've got some validation code down the bottom. And we can also just visualize it. So we can visualize how our model is performing just on our on the training set. So again, we could do like smarter training. I think one of the best notebooks at the moment, they train things sort of iteratively, so it doesn't learn really close to just the training data. So ours actually does a pretty good job because it's trained on all the training data, but you should do things like leaving out some of the data and then bring it back in for validation, so that way it doesn't overtrain it. So you can see the predicted biomass that we made fits the actual biomass pretty well for low values. As you get higher, it sort of deviates away. So that's interesting. You can use that knowledge to improve the model. But yeah, it does a pretty good job for the training images, and these are the features that were actually important. But again, like the features are, they don't, in our case, they don't mean anything. They're hard to put a real world use case to. But if you had an actual science problem, then these models are really powerful because they can tell you, oh, look at that, like smoking is related to heart disease. There's a very strong correlation between those things. So that can be really useful. Okay. Then finally, yeah, we make our submission file and click submit. So I'll do that. Run that. Hopefully it makes a submission file. Very good. Yeah, there's some model validation. And that's it. So that's the end of the code. So let me, it's made our submission file. I can view it on the side here. Is it? Yes, there's my submission file. Fantastic. And so I can let's submit it. I'll turn the internet off. It doesn't matter though, I think, because I don't use the internet. And I'll click submit. Cool. And we'll see how that goes. All right, that was a bit of a crash course. There's a lot to take in. Kaggle as a platform. There's all this computer vision stuff and machine learning approaches, which is many semesters work at university done in an hour and a half or so. But are there any questions? Why choose the second last layer? Any suggestions on this layer selection, or maybe try each layer feature? Okay, great question. So it depends on the model. So these models that are trained, do we have? How do I do that? I do it down here. Yeah, these models that are trained, the very last layer is the I think it's called the dense layer or something, and that's the one that actually is your predictor classes, so basically every model has that, and then every model, the second last layer is the average pooling layer. And I don't know exactly what that does, but it brings all the other features together. So the short answer is like, no, you have to use that last layer. I think you could probably pick it up at any other point and be like, oh yeah, from this point, I want to do other things. So maybe you could, yeah, now that I'm thinking of it, but they're probably the richest features. What some people do is they chop off, half of efficient net, and then they'll build from halfway because they think there's like a better approach. But that's beyond my computer vision understanding. Yes, you can definitely download the second notebook. The second notebook is this one. I recommend downloading that one. And it took 3 minutes without GPU. Hey, that's pretty good. Yeah. So is it still submitting? So mine's still running. And yeah, just going back to, where's the competition? Oh, I'll find it here. Okay, so yeah, if you want to look at the code, the sort of best notebooks on there, let's have a look. Most public score. They can be very overwhelming. Like I said, I downloaded them into Gemini and said, like, can you please explain this to me? How they're doing it, what they're using, and everything. And this person's done a great job of explaining the competition, and you'll find other competitions. The community is fantastic. They all write like these notebooks. One of the new features of Kaggle is actually competitions that they're not necessarily like a scoring competition. It's just a data exploration competition, and so more like a hackathon sort of thing. And so yeah, they've said this thing that I briefly mentioned, that the dry total is equal to the dry green plus the dry dead plus the dry clover, and the GDM is equal to the dry green dry clover. So you can use that to your advantage. We train 5 models. You really only need to train 3, and then you can mathematically calculate the other ones. And this person has also brought into account the targets. So the weighting of the targets that Chiu discussed, and how so the scoring makes a difference. Their image sources are 2000 by 1000 pixels, so to preserve the fine-grained details like clover leaves that would be lost to resizing the entire image, which we didn't do. They did these patching method where you can cut it in half and then use those 2 halves and then resize it from there. That's fantastic. And they used a 5-fold cross-validation strategy. I don't think, we didn't do any cross-validation. And what are they using? So that they're using a multi-head convex tiny connext tiny with pre-trained image net weights. And so they fuse these models together, and they're using data augmentation as well. So there's all these little tricks that you can do to improve things. There might be completely different methods that you can use to improve things as well. And they're using PyTorch. So it is interesting to sort of understand what's going on here. But yeah, the code can get overwhelming, I think. So keep that in mind. All right. Any final questions from what supposed to use one of the models in Kaggle for species and then use that as part of the prediction? Oh, I could do that somewhere in that model library. I saw someone, short answer, maybe. Yeah, I saw someone, so in the models here, someone was using highly-curated. So whatever model this is, they may have trained it themselves actually, but so they've retrained it on, so they've retrained EfficientNet on biomass specifically. So there could be, so maybe look up something like grasses or biomass, and you might find a model that's more relevant and has a better understanding of grass. biomass model basic here. Maybe they've trained something like that. All right, so I think that brings us to the end. So thank you very much for listening to us for 2 hours, and yeah, good luck in your Kaggle adventures. Feel free to reach out to me if you have any questions, especially if your university or something wants to has a good data set and wants to run something. Let us know and we can sort of help you make that happen. Or if you're working on a particular problem or something and you want to find the right approaches, happy to help out where we can. So thanks very much, everyone, and we'll see you next time.